Swayam Prabha. Digital India. Educated India.
Dear friends, welcome back to one more lecture on engineering system design. In the last few classes we have been discussing about the modeling techniques employed for engineering system design, what kind of engineering methods can be used at various stages of system design. We discussed about the data modeling, process modeling and behavior modeling, and today we will talk more about modeling of physical systems, especially the dynamics of physical systems. Whenever we make some product or whenever we design a product, we need to look at the performance of the product even before we really make it. So in order to make sure that whatever the product we are designing should work as per the requirement, we need to create some models and then test it and ensure that it actually performs the way we want. In some cases it may be a simple just to check the shape and its weight and other features, but in some other cases it may be the performance parameters like the acceleration time or the deceleration time or the time to reach a particular state, or what will be the maximum attainable parameter we can achieve. So these are the things which we need to analyze using models. So the modeling and simulation, basically the system modeling and simulation looks at the possibility of developing models for the physical systems and testing them through simulations to study their behavior. We can actually use various kinds of modeling techniques. You can use the physical modeling or iconic model, where you actually we make some small prototypes and then test them, or we can actually do some experiments, simple experiments and then study the behavior, or we can actually create some mathematical models and apply some non-mathematical techniques to simulate it and study the behavior. So there are various ways of doing this modeling and simulation. We will look at some of these methods and then see how this can be applied for system engineering. Of course the focus of this course is not to go into the details of these modeling techniques, but basically to tell you that these are the modeling techniques existing and what are the basic principles applied for such modeling methods. So we will be briefly going through these methods, but not into the details, or in-depth study will not be carried out. If you want to know more about those methods, you can always refer to some other courses which are readily available, or methods available on the web, or there are some video courses also available. So you can use any of these resources and learn more about these methods. So let us look at the methods existing, or we need to see why we need the models and what kind of models can be used. So here the uses of models in engineering are basically to seek answers to some of the questions. Will the system as designed will work? So we are designing some system and we need to see whether it will really work or not, and which of the two system designs is the better. Suppose you have many designs or alternatives are existing, so which one will really work, and do I adequately understand the system, and as well as what kind of trade-off I can have. So these are the basic purposes of making the models. So we need to check whether the system will work, or whether they understood the system completely, or whether we can have a choice between two models, or whether you can have a trade-off in some of the aspects. So this can be studied using engineering models. And coming to the methods of modeling, we have various methods of modeling the system or the physical systems. So we can go for a heuristic modeling, basically depending on our own heuristics and our own intuition and imagination, we can actually create the models and then test them to see the behavior. And the other one is known as the mathematical modeling. In mathematical modeling we can actually write down the mathematical equations corresponding to the physical model and then study the behavior. Another method is known as physical system modeling or bond graph modeling. So you can see the physical system modeling method is bond graph is one of the methods of physical system modeling. And in this bond graph method we normally what do is we look at the physical system and develop the corresponding model which actually have a one-to-one correspondence with the model, and that is easy to understand, and this method is used for multi-domain systems when you have a system with various disciplines like mechanical engineering, electronics, communication, software. So for such systems we can use the physical system based modeling, but bond graph is one of the methods. Then there are other methods like dimension analysis, then numerical modeling. You might have heard about finite difference and finite element methods, and these are the modeling techniques we can employ for modeling of the system. And then once you have a model, whether it is a mathematical model or a physical system based model, you can actually use it for simulation, and we can carry out the time domain analysis as well as frequency domain analysis to find out the behavior. So the model is basically converted to a simulation model, the physical system model or the mathematical model will be converted to a simulation model, and using the simulation model we can predict the performance in time domain or in frequency domain, and then see what kind of parameters we need to modify in order to get the desired performance. So that is the use of modeling and simulation in system engineering. So this is normally used when we go for the actual design of the system. So initial design stages like functional decomposition and the design of architecture, we do not go for this kind of analysis, but when we really make the design the components and the subsystems, we need to check the performance of these components and subsystems, then we go for this modeling and simulation and then analyze the performance. Let us go through one or two modeling methods to show how this can be used for our applications. Heuristic modeling, as I mentioned, it is a common sense or minimum cost physical modeling. So here we do not go for any detailed modeling of the system, we apply some common sense or make some simple models using minimum cost as a criterion and then develop the model. So that is the heuristic modeling, common sense or minimum cost modeling. I will just tell you a case study where this kind of minimum cost physical modeling can be used. This was a real situation or a real project where actually some common sense modeling was applied to get the work done without going for a detailed analysis. We mentioned about the Atlas missile project in one of the lectures. So this was a project managed by US Air Force and Corps of Engineers for developing a series of family of missiles for the US Air Force. So these missiles need to have some installation support. So the installed missile and supporting equipment in a vertical underground concrete silo. So the supporting equipment need to be inserted or to be placed on an underground concrete silo. Missile to be lowered to the silo through open doors at the ground. So once you have a concrete silo, we need to lower the missile to the concrete silo through a open door at the ground. One of the propellant lines, that is prefabricated piping sections, could not be maneuvered into the propellant system's shaft. So there was a propellant system shaft which actually should carry the propellant lines, but they were not able to maneuver this propellant system shaft through the silo or to the ground silo they created. So they tried many ways to do this, but they could not bring this propellant system shaft into the silo because the propellant lines were actually obstructing the movement of the system shaft. If they want to do the complete section, then it would have cost around $300,000 for 70 sites. So that was the problem. If they could not do this, they could not maneuver this particular shaft into the silo, then they were to redo the complete section, and for all the sites it may cost around $300,000. So they could not do it for many days and they were trying what to do with this particular problem. And then this heuristic modeling method came to their help. They created a very simple model of the pipeline as well as the shaft, and then tried on the ground many ways of inserting this into the silo. So they maneuvered this shaft under various orientations and various positions, and they could find that there is one position where actually they can bring this into the shaft, or the shaft can be brought inside the silo. So this was tested using very simple prototypes, very low cost model, and they found out the method to insert it, and then they simply applied the same principle, and then they could maneuver this shaft into the silo and could solve the problem. So this kind of modeling basically comes from the common sense of the users. The designers think about the all possibilities and then make some simple models and then create a scenario where actually they want to solve the problem and get a solution. That kind of modeling is known as the heuristic modeling. For example, if you have a large cupboard to be moved out of the room and you have a small door to be there to take it out, then we need to look at, okay, how do you actually take this cupboard out of the room. May not be possible to simply take it as it is, so you may have to tilt it some side, or you need to make some particular angle and somebody has to move forward and then take a turn, and then the other person has to come and take a turn and then tilt the table or the cupboards in a particular direction to take it out. So those kind of things cannot be modeled or simulated using mathematical methods. We need to apply some common sense technique and do this. So the same principle applies for system engineering also. We can actually do some common sense modeling and solve many of the problems which we really face on the ground when really implementing the system. So that kind of methods are known as heuristic modeling. So this kind of modeling, the physical modeling, provides a grasp of the problem that cannot be achieved by any other technique. So if you apply this common sense methods or the heuristic modeling technique, we can actually get the grasp of the problem where other methods cannot be applied, and crude models can be easily developed from basic materials at minimum cost. So in order to do this, we can actually create some crude models and using basic materials and at very low cost, and a good bit of caution needs to be applied to any conclusions reached. So whenever we do this kind of heuristic modeling, you cannot make any generalized conclusions that particular solution may be applicable only to that situation. So bit of caution is needed when we do this kind of modeling and make some conclusions out of this. So that is the first method of heuristic modeling. Then we can actually do different types of mathematical modeling also. So a mathematical model can be defined as a construct that comprises an abstract representation of a real system. Models are constructed by people often for the purpose of system design. So mathematical models are abstractions of the physical systems. When you have a physical system, we try to abstract into a model using mathematical methods, and they are constructed by people often for the purpose of system design. And then computational simulation, a mathematical model implemented in a digital computer. So once you have a mathematical model, we can implement it in a digital computer and get the simulations done. So the computational simulation is basically a mathematical model converted to the use in a computer, and where you can actually get the outputs. Of course, the law of nature, a fundamental understanding of causality in a physical system, often expressed in mathematical form or as an algorithm executable by a computer. So whenever we make the model, we need to follow the fundamental understanding of the causality in physical systems. So what causes a particular system to behave in a particular way, so that actually comes from the physics behind the dynamics or the system behavior. So we need to look at those fundamental issues and then only create the mathematical model and use them. So let us see how the mathematical model can be used in engineering system design. So most of you may be knowing how to create mathematical models. So we take an existing system or a mechanical system and then find out the abstract nature of that system and then create a mathematical model, and then see how to write the mathematical equations corresponding to the various performance parameters of the system, and then write down the equations, and later on we convert those equations into a form where it can be accepted in a digital computer and simulations can be done. So let us take one simple example, a spring mass damper system, and I will show you how to model this system using the mathematical methods. So let us take a very simple case of a spring mass damper system. So we will have a spring and a damper. So this can be a representation of any mechanical system. So if you have a spring mass damper system like this, and a force is applied here, a force of F is applied, and if this is the stiffness parameter of the spring and this is the damping parameter of the dashpot, we can actually represent the displacement of this by parameter x. So if you want to find out the displacement of the mass when you apply a force and what will be the dynamic nature of the response, we can actually model this using mathematical relationships and then convert that into a simulation model. Now if you want to know this relationship, then you can write down the equations of motion in terms of the force balance. So we have F, force F is equal to mx double dots plus bx dot plus kx, where x is the displacement of mass and m is the mass of the body, then b is the damping parameter and k is the stiffness. This is a time domain relationship. So this is x double dot stands for the acceleration, x dot stands for the velocity and x for the displacement. In order to solve this and to find out the relationship for x, so we want to find out the displacement x in terms of time domain. So xt need to be found out. We can actually change this to the Laplace domain to solve it. So if you do this, then we will be getting it as xs, that is the Laplace domain as fs over ms square plus bs plus k. So the s stands for in the Laplace domain. So f of s is the force in the Laplace domain, m is the mass and b and k. Now we can actually solve this for using standard mathematical formulas, or we can actually put this in the x omega is equal to in the frequency domain omega n square divided by square plus 2 zeta omega n plus omega n square, where omega n is given as the natural frequency is given as square root of root k by m. So we can actually get this as in the this can actually be converted into a time domain, and then you can solve this and then convert it into time domain. We can actually use any standard simulation softwares to simulate this behavior. This equation can be easily solved, you can actually simulate it. Similarly in the time frequency domain also we can get the output using this relationship. So now for any applied force F, we can find out the response of this system, the displacement of the system, displacement, velocity and acceleration can be easily obtained from here. So if you simulate this, then the response can be something like this, the time response can be obtained like this. Depending on the parameter values, you will be getting various performance parameters like rise time, then the settling time. So all those can be plotted for a given force, you will be getting a constant displacement here. So this is the transient period. So you can find out what is the time taken for the transient to die down. So transient period, and then you have a steady state period. So using these equations, we can actually simulate it. We can use the software like MATLAB or Simulink. MATLAB or Simulink can be used for simulating the behavior of this particular system. So that is a very simple system, and we are showing how the mathematical model can be generated for that kind of systems. When you have a complex system, we need to do is to take the abstract that complex system to a mathematical model and write down the equations of motion for the system and then simulate it and get the behavior. So any complex system can be modeled using this kind of methods, mathematical modeling techniques. If you have a robotic system or you want to find out the behavior of a machine tool, any of these, or even if you have a simple motor, you want to find out the performance characteristics what you design, and then you want to see what kind of response time it has, how much time it will take to reach a particular value of acceleration. All those things can be modeled and then simulated. We will get the outputs using this kind of method. So that is one way of doing mathematical modeling. Not only this, we can actually do many other things also using mathematical methods. So I will show you another one where actually we can model and simulate the traffic flow during the peak time at a traffic junction. So that also can be modeled using mathematical methods, or you can, if you want to find out the deflection of a beam, we can actually do that. If you have a beam like this, a cantilever beam, and you want to find out the deflection, suppose you apply a force over here or you hang a mass over here, you want to find out what will be the deflection of this beam. Again we have standard equations for representing the deflection. So we can actually find out what will be the deflection under various situations. Depending on the type of load, we can find out the deflection as well as the bending moment, bending stress, all those can be modeled and then simulated to get the output. There are different methods, mathematical modeling is one of the methods to get the outputs. Now coming to the traffic problem, we will see how that this kind of traffic problems also can be modeled using mathematical method. So this is the problem given. The traffic lights at road junction are said to operate with a red phase of length 100 seconds. So you have a red phase of 100 seconds. So we can put it as RG as 100 seconds. So sorry, red phase R, and then green as 60 seconds. So you have a traffic signal which actually there is a red signal for 100 seconds and green phase of for the 60 seconds. And vehicle arrive at the traffic lights on average 1 every 4 seconds. So every 4 seconds one vehicle is arriving. So every 4 seconds one vehicle is arriving, and when the lights turn to green the vehicles in the queue leave at the rate of 1 every second. So this is the arrival, every 4 seconds one vehicle will be coming, and when it is green every 1 second one vehicle will be going. So we need to model how long the green signal should be there, or if you want to find out how much delay will be there for the vehicle to go from the signal, or whether there will be any pile up of the vehicle at the signal, we can actually model it using mathematical methods, or we can actually use simple methods to model it and then predict what will be the waiting time for a vehicle when the signal is about to change, or how long the vehicle will wait at the signal, or what will be the average waiting period can be modeled using mathematical methods. So we will see how this can actually be done. So now we know that a red and green cycle will actually have 160 seconds. So we have 160 seconds for a red and green phase. So when it changes to green there will be 60 seconds, when it changes to red it will be 100 seconds. So during the green phase a maximum of 60 vehicles may pass through the road junction. Since we can actually go through 1 second is needed for one vehicle to go, so we can actually have only 60 vehicles passing through during the green phase. So 60 vehicles during green phase. Whenever the signal changes to green you can have 60 vehicles passing through. Okay, now 40 vehicles will arrive. So during the 100 seconds, so 160 seconds, so totally we have 160 seconds, so we can actually expect 40 vehicles to arrive during this phase. So we will be having 40 vehicles arriving during this phase. Initially we can have 60 vehicles passing through the green phase. So that means there will not be any pile up of the vehicle. So during one green phase all the vehicle can actually pass through the green phase, because 60 can pass through and we have only 40 vehicles arriving. And this can actually be modeled either by, because it is a simple system and it is only for one case, we can actually model it just by writing down the table and then see how many vehicles will pass without any waiting, or what will be the average waiting time for each vehicle. That can actually be modeled by writing down the table. So if we assume that 2 seconds after the signal changes to red one vehicle is coming, then 6 seconds, then 10 seconds, then 14 seconds, 18 seconds. So one vehicle will be coming at 2 seconds, another will be coming at 6, 10, 14, 18. This vehicle which is coming over here, it has to wait till the signal changes to green. So it has to wait for around 98 seconds. So the vehicle coming at 2 seconds after the signal changes to red, it has to wait for 98 seconds. So that is the delay time for the first vehicle, and for the second vehicle it will be 95, because 1 second will be for that passing of the vehicle, and then we will be having 92 seconds waiting, then we will be having 89 and so on. So we will be having the total delay period where the vehicle is coming at 1/34 seconds. You can see, if you write down the table you will see that 1/34 second this has turned to green and all the vehicle have passed. So this vehicle will be having a 0 seconds delay. Similarly till 1:58 the last vehicle also passed without waiting at the signal. So this many vehicles, so you will be having around 7 vehicles passing through the signal without any delay. So 0 delay will be there, and if you take the average delay we can actually find out the average delay of the vehicle, and you can calculate the average delay from this one. So that is one way of doing it, but this again it is writing about making the table and then calculating it. Now how do we actually convert that into a mathematical equation and then do it or generalize it for any kind of traffic problem. So here we are assuming that 4 is fixed and 1 is fixed, but if it is not fixed then how do we model it? We can actually use some mathematical equations and then model this particular delay. So we need to find out the average delay. In this case the average delay will be total delay. So we have the total delay of the vehicle divided by 40 vehicles. So we have 40 vehicles coming during the phase, so there will be sigma delay by 40, so that will be the delay. So in this case you can see that the delay will be around 41.25 seconds, that is the average delay of the vehicle. Now if you want to model this using mathematical equations, we can actually find out the parameters and then create a mathematical model for it and then use that one for simulation of the system under various situations. So whenever the RG or RV changes, so we can actually model it easily without creating a table like this. So in this case we can actually see that RV is the phase or red phase, so length of red phase and similarly GV is the length of green phase and then A is the time between arrivals and D is the time between departure. Same as what we saw there, RV was 100 and GV was 60 and A was 4 and D was 1. Now if you want to find out the average delay, is 1 over n sigma delay, that is the total delay divided by n, or n is the number of vehicles will be equal to RV plus GV divided by A. So this is RV plus GV divided by A will give you the number of vehicles and that sigma delay over n will give you the average delay. Now if you want to find out the sigma delay, the sigma delay can be calculated Sn is equal to 1 over 2 n A plus L. So this will be the relationship for average delay, where A is the first term in this that table what we saw in the previous case, that is A minus D, and L will be the last term which is RV minus 1. Now n can be obtained as RV minus 1 divided by A minus D. So using this relationship we can write Sn as RV minus 1 divided by 2 A minus D multiplied by, so this stands for the n, and then A minus D plus RV minus 1, that is the delay, and if you simplify this you will be getting the Sn as equal to A multiplied by RV minus 1 divided by 2 RV plus GV multiplied by 1 plus RV minus 1 divided by A minus D. So, this actually shows that any scenario, any dynamic scenario can be easily modeled using mathematical relationships, and that can be used for modeling that particular scenario and predicting the behavior, and depending on the requirement we can actually modify the parameter, or we can think of changing the system parameters in order to suit the requirement. So, that is the advantage of using mathematical model for this kind of applications. So, in the system design we will see many scenarios like this, where we need to find out the behavior, the dynamic behavior of that system, particular situations, and then we need to modify the system design. So, mathematical tools will be really helpful for such situations. Let us see some other methods also. So, we have a few other methods also for modeling. So, when analytical solutions are not available, we go for a method called finite difference method or finite element methods. So, finite difference method gives a point wise approximation to the exact solution of a partial differential equation. Again, these are the two methods which can be easily used for analysis of the structures, especially when we want to find out the load acting and then the stress levels, or you want to find out the temperature distribution. So, this kind of application, there are wide applications for these kind of methods like finite element method and finite difference methods. I am not going to the details of these methods because you can find many resources for learning about these methods, but just want to tell you that these methods can be easily employed for system design, and whenever the requirement is there we can apply these methods to do the analysis. Just to show you how it works, in the finite element methods the domain can be analytically modeled or approximated by replacing it with an assemblage of discrete elements. So, that is what we have an assemblage of discrete elements to represent the system. These are some examples or methods. If you have a structure like this physical system, you can actually create a mathematical model by idealization, and then you use different kinds of elements. So, in finite element method we use various elements, 1D, one dimensional element, 2 dimensional elements, or 3D elements can be used for modeling. There are various softwares available for doing this. So, you can actually conversion of the physical system to a mathematical model is the first task. Once you have this, then actually you can use standard software for simulating it and finding out the behavior. And these are some other examples. These finite element methods are widely used in design activities. So, for the especially in case of aircraft design, missiles and all. So, basically when you do the meshing you will be getting a structure like this, you will be having different elements, and we can find out the stress or temperature or any other parameter using from these elements, and then you can plot it to find out how it will be affected by various parameters. So, this is a finite element model of an aircraft. And the last system I would like to discuss is the bond graph methods. As I told you, bond graph is a physical system based modeling technique. So, here we look at the physical system, we do not convert that into a direct mathematical equation. What we do is we will try to create a graphical representation of the physical model, and then using a method called bond graph we can actually represent the physical system directly and then can be simulated. So, this was developed by a person called Painter long ago, and it is widely used by professionals, and there are few softwares available for using this method to simulate the particular system when we model the system using bond graph. So, here in bond graph method the exchange of power between two parts of a system has been considered. So, we always assume that whenever there is a system there will be some exchange of power. So, the power interaction between the elements is considered here, and that is why sometimes it is known as power bond graph method also. The flow of power is represented by a bond. So, whenever you have an exchange of power we represent that by a bond, and effort and flow are the two components of power. So, there are two parameters we need to define to get the power, that is the effort and flow. The main difference between the classical approach for modeling a physical system and the bond graph modeling is shown here in this diagram. As you can see here, in the classical approach for modeling, we start with the physical system and then we create an engineering model using some mathematical methods, or we convert that into a simplified and abstract model, and that is the engineering model, and then we write down the differential equations corresponding to that model, and then we use some standard methods like block diagrams and then simulation language to simulate it and get the outputs. But in the case of bond graph modeling, we do not go through these stages, we skip some of these stages. We have this physical system, then we create an engineering model using converting of the physical system by abstracting that to an engineering model, and then we create a bond graph. So we do not write down the differential equations or we go for the block diagrams, we convert the engineering model to a bond graph, and then this bond graph will be used in the computer through some software and simulated, and we will get the output. So that is the difference here in bond graph modeling. We do not need to know the differential equations corresponding to the particular model, or we do not really need to worry about what kind of equations to be used, how to solve these equations. So all these are done using the bond graph method. The only difficulty is that we need to know how to create the bond graph for this engineering model. No direct equations here, only the graphical representation. So we will create the bond graph from the engineering model, and it will be used for generating the differential equation through the software. So the software can actually do the job of creating the differential equations and then simulating it. So we do not really go into this part of this modeling in the bond graph method. So that is the advantage of using bond graph modeling. Okay, so the method used in bond graph, we need to learn some of the basic elements used in bond graph in order to understand how the bond graph modeling can be used for system simulation, or how the engineering systems can be simulated using bond graph. There are some basic elements, as I told you, there is a parameter called effort and flow, and apart from this we have many other generalized parameters. What we do today is to look at those generalized parameters, and then we will stop after seeing the parameters, and then we will see how to use these parameters in the system modeling in the next class. So I will just explain you about the generalized variables. As I told you initially, the power variables are effort and flow. So you have a effort variable and a flow variable. Effort is represented by E and flow is represented by F. So this is the effort representation E, and flow is denoted as F. Then we have two other parameters known as energy variables. The energy variables are the momentum and displacement. So the momentum is represented using P and displacement is denoted by Q, and there is a relationship between these P, Q and E and F. The power flow in the system is given as power is effort multiplied by flow. So whenever there is a power flow taking place, that is actually a product of the effort and the flow. So whatever may be the effort and flow, the power actually can be calculated by taking the product of this effort and flow, and this momentum is basically the integral of the effort. So P is obtained by integral E dt, and similarly Q is obtained by integral F dt, that is the integral of flow gives the displacement and integral of effort gives the momentum. So integral of effort gives the momentum. As you can see here, this is if you take the variables, you can represent them in various domains. As I mentioned earlier, bond graph is basically used for multi-domain systems, and you have mechanical systems, electrical system, hydraulic system, and they are combined. We need to have a common language to use for modeling. So here the effort and flow are common in all the domains. So whatever may be the domain, whether it is mechanical, hydraulic or electrical, we can use the same variables effort, flow, momentum and displacement. This chart shows the variables effort and flow and different domains. So you can see the electrical domain, the effort is voltage and flow is current, and voltage into current will give you the power. So multiplication of the effort and flow will give you the power, and in translational the force is in the translational motion, the force is the effort and velocity is the flow, and rotational motion torque is the effort and angular velocity is the flow, and in hydraulic pressure is the effort and volumetric flow is the flow. Similarly for chemical potential and molar flow, thermodynamics, temperature and entropy. So as you can see here, whatever may be the domain, we can still represent the effort and flow, and that actually helps us to have a common modeling language for multi domains. So I would like to stop here today. We will see the methods by which how do we actually use the bond graph for modeling the engineering system, and what are the basic modeling elements used in bond graph. We will see all these details in the next class. So till then, goodbye to all of you.